Hello, welcome to another lecture on control. In this lecture we're going to talk about discrete PID control. So what I'm going to run you through initially is I'm going to just give you a recap on continuous time, move on then to difference equations, and then discretization methods of a PID controller, so the various methods you can use, and then we'll focus on the backward Euler approximation for the derivative and the trapezoidal rule approximation for the integral, and then I'll show you the overall form of the discrete PID. And a quick check-in question just to understand that you've understood the discretization method that I've run through. So after this lecture, you should be able to explain the method behind obtaining a discrete PID controller based on a continuous time PID. So if you recall back from continuous time, when you had a PID controller that looked like this in continuous time, so in terms of the feedback control system, negative unity feedback, negative unity because you assume an ideal sensor, errors formed by reference take away or minus the measured output, that forms your error, and your error multiplies by these three terms. So here you've just got your proportional control gain, so Kp, your integral, which is Ki, multiplied by 1 over S, so that's effectively your integrator, and S, where S is effectively your rate of change, so your derivative. And then that multiplies by Kd. So if you remember back to continuous time, that's pretty much your form. So you're looking at effectively the area of the error, the rate of change in the error, and then just having this multiplier. And effectively what you do is you tune these Kp, Ki, Kd to give them values for a certain application depending on what your system is, and it'll give you your effectively, if it's well tuned, it'll perform as you expect, and it'll compensate for things such as disturbances, maybe wear and tear on the system. So these three terms combined are very, very powerful for getting a system to behave in a desired manner. Okay, so your reference is what you desire, system output is what you actually get, and what you're doing is effectively configuring the continuous controller, in this case, to give you that desired performance. So if you recall back where we had, we effectively used differential equations involving derivatives of functions. So in this case, here we've got y of t, which is just the output of the system. So the slope or gradient of the point is given by this. So effectively the Laplace transformation of dy of t over dt, when you undertake transformation, becomes s, because d over dt is s, capital Y of s. And it's the same for the error function. So if we look back at the error function here, it's formed, as I said, just the reference take away minus the error, and then we get this error function here. Okay, so you can see all the signals are obviously continuous as we'd expect. So then again, it's just the Laplace transformation, d of t, d e of t over dt, and that just becomes s, because d of t, e of s. So now if we move on then to looking at difference equations, so because we're now moving on to the form of a sample data control system, so just to recap remind you of this diagram. So when we're looking at kind of a mixture in practice, we're looking at a mixture of continuous and discrete time signals, where obviously in practice we're saying the system is continuous and the controller, which is normally a microcontroller, some form of computer, microprocessor, is digital and it works in discrete events, so hence you have to sample the signals that come in, hence, or i.e. sample the signal from the continuous sensor or sample the signal from the reference. Okay, and you form this kind of sampled error here. So go back to the video if you kind of stuck and you're getting a bit confused by this diagram. Go back to the sample data control system 0 to hold video if you want initial explanation behind this video, behind this pictorial representation of a sample data control system that you can see. So in terms of the samples, if you remember, I told you that this z here is a time shift operator. So if we do z e of t, that effectively is e of t plus 1. So it's e of t plus 1, so it's effectively one sample ahead that you'd be looking at. So t plus 1. Don't get the notation confused here, thinking that I mean time. Effectively t plus 1, I just mean one sample ahead. And then what we can then look at also is the backward time shift operator. So if we now use z to the minus 1, where z to the minus 1 effectively means t minus 1, it gives this. So z to the minus 1 multiplied by e of t is equal to e of t minus 1. Where you can see now what we're looking at is that we're looking at the past one sample. So effectively, we're looking at the sampled error, or the previous sampled error, one sample interval ago. Okay, so in terms of practice and in terms of a PID control system, the backward time shift operator is important. That's the one that we want to use, because what we have in the control system is past known or captured information from the operation of the system. You can look ahead using further kind of control strategies, but within this initial teaching, we're going to use the backward time shift operator. So looking one sample or more behind, or knowing kind of past information. So again, if I'm going to go back, and if you recall from when we looked at model-based design for embedded control, so again, go back and look at that video, that there was various methods that we could go about to kind of develop a discrete control there. So continuous system, you design a continuous controller based on a continuous system, and then discretize, and this is effectively what we're going to do within this lecture. You discretize it and get yourself a discrete controller. Okay, so you end up from C of S to C of Z. Another method that you can do is you can get your continuous system, discretize the continuous system to get G of Z, so a discrete system, and then you can design your controller based on G of Z. So that's another way that you can go about doing this. So known as direct digital control. We won't cover this initially in this series of videos though. So in terms of method, there's various methods. So in terms of the ones we're going to go through, we're going to look at the backward Euler approximation to the derivative term, and the trapezoidal rule approximation to the integral, or the integrator. Other methods though, so you've got ones you could call forward Euler approximation, Tustin's binary approximation, max pole zero. And if you want an additional task, a little bit of extra work, go away and look into these methods and see how they compare to the methods that I'm exploring or introducing you to in today's lecture. So I'm going to first of all go through the backward Euler approximation. So if you're looking at in terms of the time domain, you've got dE of t over dt, and that is equal at the sample point to this formula here. So 1 minus t minus 1 multiplied by et. So this is if we're looking at this, and then it's divided by ts, and that is effectively here, if we're looking at this graph here, we've got e of t. So e of t multiplied by 1, it's going to give it et. So that's effectively that sample point there, minus e of t minus 1, which is at that sample point there, and then divide by ts. And what that's effectively given us is it's given us an approximate derivative in terms of the midpoint of these 2 points. So it's effectively taking the mean of these 2 points and determining that point there. So the width is ts. So what that's telling us is effectively we've got a delay of half a sample in terms of the information that's been provided. Alternatively, you could represent it in this form, because if you remember, e of t minus 1 is effectively z to the minus 1 multiplied by e of t. And noting that z minus 1 represents a delay of one sample. So effectively here we've got a delay of half a sample. So in terms of if we're looking at here we've got a continuous time PID controller in the S domain. So kp, k subscript d of s multiplied by e of s. And this is also given here in the time domain. So if you're not sure about how to go about these transformations, have a look at your notes and get familiar with that. But what we've done, we've effectively taken equation 1.5, so the one we've just derived, and we've substituted it into equation 1.7 to effectively give us this here. So you can see that. And that's kind of here, I've just e of t is outside, I've just multiply it across, and this is the formula you'll effectively get. So all you can see is I've just replaced d of t dt with this formula here that effectively works out the midpoint of the two sampled points, so the current and the previous sample, and it takes an approximation midpoint of those 2 points. So that's looking at your rate of change. This can be written in this form. So if you were looking at this, what you would kind of, well, effectively just multiplying it through, so we can effectively separate kd e of t, that, and then kd over ts e t minus 1. So getting that. So it's up to you. You can put it in that form. And then what you can do, obviously, e of t here is common, so you could just move that outside, put brackets, and then move it outside the brackets. So that is your backward Euler approximation for the derivative. Now I'm going to look at the trapezoidal rule approximation for the integral. So this is effectively the integral of e of t, so it's the area under the curve. So if we're looking at this now in terms of, that's effectively what we want to do, is we want to get an approximation for this area. So it's quite simple mathematics, and we can approximate this using the trapezoidal rule. So the area in between samples is the integral of the interval t minus 1, so that's your past sample, to t. So the area is approximated by this equation. So e of t, so effectively that, plus e of t minus 1, divided by t of s, so the width of that, and then divided by 2. So it's effectively, as it says here, it's the mean of the two vertical heights. So it takes the mean of the two vertical heights multiplied by the width, and that's effectively going to give you the area. Alternatively, you could write it in this form here, but given by equation 112, because we can just assume that e of t minus 1 is equal to z minus 1 e of t. Where in that case, obviously, e of t is common to both of these. E of t is e of t, e of t. So we can move that outside the brackets and put it in that form, and then just move the 2 underneath the ts. So what we're looking at now, so we've kind of got, this is our new trapezoid. So if we go back to the previous, you'll see we worked out the area of that. And effectively, we've taken another sample, and this now is it's the previous one now becomes the one on the previous side now becomes our previous integration. And now we've got a new trapezoid. Okay, because you've got t minus 1, t minus 2. So in terms of representing this in the mathematics, we're now considering the past sample t minus 2. So the area of the past two intervals becomes effectively this. So you'll see this part is identical, this first part is identical to what you've just seen. And then we've got this additional part here, so e of t minus 1 plus e of t minus 2 multiplied by ts, so the width, divided by 2, because we're effectively just after a midpoint, the midpoint here. And that there describes, in terms of working out the area of in terms of the current, and then the past two known measurements. It can alternatively be written in this form, because we can move the effect of the 2's outside, and then just close the brackets, so ts over 2, and then close the brackets for the whole expression. And then you see e of t, which is here. And then what you'll notice is you've got effectively 2 e of t minus 1. So 2 e of t minus 1, hence that 2. And then you've just got your 2 e of t minus 2. So that's the form that you end up with here. So based on what you've just seen, if we take this a step further, if you can imagine that we've got a sample interval maybe of 0.1 second, and we're continually taking samples, there's continual past information, and we've got areas of trapezoidals the area being measured, well, the formula would look like this. So you can see in the case up to this point, it's for the past the current and the past 3 measured values. And then you can continue, the pattern just continues plus t minus n, which n is just the number of the past sample. So this is effectively approximating the whole integral of the error signal. And you can imagine that would be incredibly computationally intensive. Okay, if you're sampling very, very quick. So we don't really want to be doing that in terms of to get us decent control. and we want nice kind of quick to compute algorithms on board our digital controllers. So what we've got now is this equation 116, and what you'll notice is we've got this previous subscript int, where this is effectively all the previous integrals past. So if you imagine, if we go previous, if you go here, so we've got this area and this area being determined based on this, and then you imagine if the controller had sampled maybe 10 times, then it's got all those, it's got more than what here in terms of the past integrals. So what the area in terms of the previous ones, what it's done is it's summed in this previous int. Okay, so if you imagine sample, right, work out the first trapezoidal, sample again, work out the second one, or which is the new trapezoid, sample again, and then the first one worked out then gets added here, and then obviously the new area calculated, sample again, new area calculated, and the previous one then moves to here, sample again, and the new one moves to here. So it's effectively given by this, where previous int is updated. So previous int becomes previous int, and then this kind of these two previous, the kind of effect of the new trapezoidal and the previous trapezoidal, and then this is continually updating as you sample, and the overall thing is obviously changing as you sample. The cycle just effectively repeats itself. So in terms of if you're just looking at the PI controller, this is what it looks like in the continuous time domain, and this is in the time domain. So you remember this, what we looked at in terms of the form at the beginning, where you've got here just your integral of e of t. So what we've done here is we've effectively replaced e of t with the equation in terms of 117 that we've just determined, replace it in here, and then this is the form here that we get for equation 119. So that is the form there of the proportional and integral controller. Then the full form of the discrete proportional integral controller is given by this form. So u of t, so the control input, is kb e of t, which is just as you'd expect. The proportional doesn't change because it's just multiply the error. Ki, and then here you've got kd over ts. Okay, I've just moved the ts over here, and you can see then this is the form that you've just determined, and then this is effectively working out in this part is working out the area of the past two trapezoidals, and then that's the previous int for any previous areas that have been determined, and the derivative here is where you're effectively just working out the midpoint of the two sampled, so the current and the past sampled measurements, or sampled data, sampled error. So in continuous time, the PID controller has two zeros and a pole at the origin. In discrete time, the controller has two zeros and a pole at 1, i.e. on the unit circle. So again, you're noticing this mapping between this pole being at the origin and the mapping between that and the pole being at 1. So you've seen that a few times so far. So a quick checking question. So I just want at this point to ensure that you are, or to make sure that you're aware of how to discretize this continuous time PID controller equation. So what I want you to do is explain the process of discretizing an integral. In this case, we look at the trapezoidal rule, and the derivative where we look at where we use the Euler approximation. And then I want you to write down an overall expression for the discrete time PID controller. So I will create the video solution for this. So if you check back, look and you'll see the video solution for that. So in terms of summary, I've introduced you to the backwards time shift operator, so capturing the past one sample, or further you can capture the past 2, 3, 4, whatever. And then I've introduced you to a method really for discretizing a continuous time PID controller for the derivative, so the backward Euler approximation, and also the integral, the trapezoidal rule approximation. There are further methods that you can look into, as I mentioned earlier. So if you want to do so, please do so and compare them to the methods. So I hope now at the end of this lecture that now you can explain the method or a method behind obtaining a discrete PID controller based on a continuous time PID. So if you have any questions, please feel free to email me. So have a nice day. Thank you.